Welcome back to another Algebra 2 lesson as we continue the FG.2 notes as part of Unit 2 dealing with functions. In FG.2 notes part 1, we took a look at slope-intercept form of linear functions. In part 2 here today, we are going to look at point-slope form of linear functions. So the difference between these two is essentially the implication of the name. The name slope-intercept form gave us an equation where we needed and used the slope and the y-intercept to come up with an equation for a line. Those were the two pieces that were included. In point slope form, now we're using a point in the slope to come up with the equation of a line. That's the information that we're going to use. So point slope form goes by the equation that we see here on the screen. Y minus y1 is equal to m times the quantity x minus x1. And this is for any point that has an has coordinates x1, y1, and has and dealing with a slope m. So we've seen the slope m before, and now instead of a y-intercept, this could be any point. So the two things we need are a point and the slope. So in problem 7, it says write the point slope equation for a line that passes through -3, 3 and 0, -1. So for point slope form, again, we need a point. We have 2, and we need the slope. It does not give us the slope. But remember, we know how to find slope. Slope is equal to the change in y over the change in x's, or y minus y over x minus x. So what I can do here is I can take 3 and subtract -1, the y values in the numerator, and then take -3 and subtract 0, the x values in the denominator. This would give me 4 over 3, or -4 over 3. This is the slope for the line. So this is our m value. Now, in order to write the point slope form, the only other thing that I need is a point. So I can write it in two different ways already because I have 2 points. So what I would do here is, let's use the point -3, 3 first. So I would have y minus the y value of that point, 3, equal to the slope, -4/3, times the quantity x minus the x value of that point, which would be a -3. So instead of writing this as minus a -3, I will write this as x plus 3. And this is point slope form for the equation. Now we could also write it with the other point. So we could use this second point, 0, -1. So in this case, it would be y minus -1, or y plus 1, equal to -4/3 times x plus the x coordinate, which is 0. So we could just write this as -4/3 x. Either of those would be acceptable ways to write point slope form of this equation. So writing the equation is probably a little bit faster in point slope form than it is in slope intercept form because we don't actually have to solve for the y-intercept. We can also graph these using point slope form. So it really gives us all the information that we need. The first thing that we have to do if it's in point slope form is we need to identify the slope. So the slope for this specific problem is the same as it was before, actually. The slope is -4/3. The other thing that we have to do is identify identify the point. So we need an x value. The x value comes in from the parentheses. Notice that this was x minus x1. But what we see here in parentheses is x plus 6. So in order to have x plus 6, x of 1 had to be -6. So this point would start with -6. And then the y value comes from y minus the y value, so y minus 1. So if we want to graph this, we can graph our point, -6, 1. And then we can plot additional points using the slope. So we would go down 4 units, 1, 2, 3, 4, and over 3 units, 1, 2, 3. Rise over run gives us slope. Same thing, we could continue doing that down 4, 1, 2, 3, 4, over 3 units, 1, 2, 3, and that would actually give us the y-intercept here. We could continue plotting points, also maybe potentially going in the other direction. So up 4, 1, 2, 3, 4, and left 3, 1, 2, 3. And you could plot as many points as you could fit on that grid if you wanted to. And as long as we have more than one point, we have 2 or more points, we can draw a straight path. And there we have the graph for point slope form. So this is really the only difference between slope-intercept form and point slope form. Point slope form, all we need is a point. We don't actually have to find the y-intercept. And then we pair that with a slope to put it into the equation. Now we did look at some examples in slope-intercept form where we talked about finding an equation of a line that was parallel to a given line, or perpendicular, or where we combine some information to write equations. We can do all of these things with slope-intercept form as well. It just gives us a second option or a different way to write an equation. Now, the reason we use slope-intercept more frequently is because it serves a better purpose in terms of applications. So let's take a look at problem number 9. Problem number 9 says, in meteorological studies, atmospheric temperature depends on the altitude according to the formula T equals negative 3.5 H plus 58.6, where T represents the approximate Fahrenheit temperature at the height H in thousands of feet. First thing it says is interpret the meaning of the slope in this context. So if we want to interpret the meaning of slope, we probably need to know what the slope is. So remember, this is in the form, if we take a look at this, this is in the form of slope-intercept form, y equals mx plus b. So in this case, that means the slope is negative 3.5, or if we wanted that in a fraction, negative 3.5 over 1. The reason I'm going to write this as negative 3.5 over 1 is, remember, this is the change in the y's over the change in the x's. Or in this specific case, we could basically think about y as t, change in t over change in h. So if I write it of this form, change in t over change in h, now I can break down what really is going on here. So change in t is the numerator is negative 3.5. Change in h is the denominator is 1. So T represents the approximate Fahrenheit temperature. So what we're having is a drop or a decrease in the temperature by 3.5. And let's put in our units, degrees Fahrenheit, every 1 hour, or every time the hour increases. So every hour there's a decrease of temperature by 3.5 degrees Fahrenheit. And so that's basically what the slope means in this context. So if we can take that slope into change in y over change of x and represent change in y and over change of x in terms of our problem, then we can take this number and see what the number actually represents. In part B, it says determine the altitude needed to reach it. Sorry, determine the temperature at an altitude of 12,000 feet. Remember that, sorry, we have a mistake here. Let's go back to what H actually means. Sorry, in problem A, H does not mean hours. H means height in thousands of feet. So in this problem, it's actually a decrease in temperature. It drops 3.5 degrees Fahrenheit every 1,000 feet. Whereas we go up every 1,000 feet, the temperature goes down 3.5 degrees Fahrenheit. Sorry, so H actually represents height in thousands of feet. So that's key information there. Now let's look at B. It says determine the temperature at an altitude of 12,000 feet. So remember height is h, and height is in thousands. So if this is 12,000 feet, this actually gives us h that is 12. So basically what we want to find is what is the temperature when h is 12. So we can do a simple substitution here, put in 12 for h, and then evaluate the expression. You could do this by hand if you would wanted to, but let's go ahead and pull out that graphing calculator. So what we have is negative 3.5 times 12 plus 58.6, and we get a total of 16.6. So the temperature is going to be 16.6 degrees Fahrenheit at 12,000 feet. So we want to make sure we add some context back into that equation. But finally, part C asks to determine the altitude needed to reach a temperature of negative 10 degrees Fahrenheit. So now we know what the temperature is. The temperature is negative 10. So now I can substitute for T. Negative 10 equals negative 3.5 H plus 58.6. And in this case, I want to solve for H. So what I need to do here then is move this 58.6. So subtract 58.6. So this would be negative 68.6 equal to negative 3.5 H. And then let's go ahead and type that into the calculator. Our next step, sorry, here would be to divide by negative 3.5. Divide by negative 3.5 on both sides to get H by itself. So I'll do negative 68.6 divided by negative 3.5. And there I have H. H is 19.6. Now, let's put this back into context. The context, remember, is that H is in thousands of feet. So it's not just feet, it's in thousands of feet. So this would be 19.6 thousand, or determine the altitude needed to reach a temperature of negative 10 degrees Fahrenheit. That altitude would need to be 19,600 feet. Okay, so we've solved linear equations here, and linear functions or solved linear equations, and linear functions are essentially linear equations. So we can solve these algebraically. Now we've also thrown in graphs. So the second way that we can look at solving these is graphically. If we have this graphing calculator, the graphing calculator is going to give us a very good representation of what we want to do. So the first thing that I'm going to do here is I'm going to input my function into the graphing calculator. When I do so, I'm going to use x because it's only going to graph it if I use x as the independent variable. So I'm going to type in x for h, and now I'm going to graph. And so most of yours, if you just hit the graph, it's going to look like this. Nothing. So what we want to do is make sure that we set some parameters. Let's go to the window key. And let's change the x minimum and the x maximum. So let's go ahead and set the x minimum to a 0. The reason we're going to set the x minimum to 0 is because height can never be less than 0. So we're going to go ahead and set that down there. We know that the x max needs to be at least 12, probably higher than 12, because in this place, again, x is the h, and to answer question B, h has to be at least 12. So let's go higher than 12. Let's go ahead and make this 20. And then let's hit the zoom key and go down to 0. What this is going to do is going to fit the graph to an x value of 20. Now, we've already solved this algebraically again. I'm just giving you another way that we can solve this here. So what I'm going to do is I'm going to sketch this graph. I'm going to need an x-axis, and I'm going to need a y-axis. And then put this graph in blue. It looks something like this. Okay. So we're just going to draw a rough sketch here. It does go continuously to the left forever. We don't need to go continuously to the right forever on the x-axis because that would be h less than 0. So This is 0. We know that. We know this is 58.6. That's the y-intercept, and that's a pretty good enough labeling for the graph. Let's go ahead and give our axes some labels, though. Remember, the x-axis was height. So this is going to be the height or the altitude, and this is in thousands of feet. We also want to label the y-axis. So the y-axis here was T, which is the temperature in degrees Fahrenheit. So we can use this graph then to solve. So if we wanted to solve B, determine the temperature at an altitude of 12,000 feet. Remember, 12,000 feet would be 12 on the x-axis. So how we could solve that is we could hit the second key and then go to trace, which takes us to the calculate menu. This is an x value, and so we're just going to select value. And we're going to type in the x or the h value in this case that we want. And so it's going to give us a point on the graph, and then 12, 16.6, we can label on that graph. And that's essentially our work. That's all the work that we'd need to show or be required to show if we wanted to solve this graphically. We'd sketch the graph, we'd label that point that we found on the calculator, and now we know that we can add context. The temperature is going to be 16.6 degrees Fahrenheit at 12,000 feet. If I want to solve C, this is a t or y value of -10. So if I know the y value, what I have to do there is graph another line and find the intersection. So I'm going to go to y equals. I know my y or my t value again is -10. So I'm going to type in -10 here, and then I'm going to graph. And they cross. Where they cross is going to be my solution. And so to find that solution, I'm going to hit second, trace. I'm looking for where they cross or where they intersect. That would be problem number 5, or option number 5. It's going to ask for the first curve. I'm going to go ahead and bump my cursor down close to this intersection, making sure it's on one of the lines, and then hit enter. Then it's asking for the second curve. I can move left to right to move it closer to that intersection if I want. I don't necessarily need to. Just make sure it's on the second line. Hit enter. When it says guess, I don't really ever guess. You don't need to guess. You can just hit enter. And then your calculator is going to find the new point. So we could put this point down here. This point would be 19.6, -10. And there's our work. So it will take an altitude or a height, the x-axis of 19.6 or 19,600 feet to reach a temperature of -10 degrees Fahrenheit. So you could either solve this algebraically like we did over here on the left, or you could solve this graphically like we did over here on the right, and then we want to add context as we end the problem. For my school level guys, this is where we're going to stop where your notes stop. So if you would like to, you could take a look at problem number 10, but this is not part of your notes. Problem 10 will advance to with all of my honors guys. The final problem in the packet says 5 years after purchase, the auditor of a newspaper company estimates the value of their printing press is $60,000. 8 years after its purchase, the value of the press has depreciates or had depreciated typo there, to $42,000. So what we first want to do is find a linear equation that models this depreciation. So we have to come up with our own equation to represent what's occurring here. So in order to do that, we need to take a look at the information that they give us. And we need to figure out what our independent and our dependent variables are going to be. Our independent variable, or our x-axis in this case, should be years. And so we could just, actually, I'm going to call it time and let it be t. So let's let t equal time. And that's going to be my dependent variable. And then let's let v equal value. And so this is going to give us any points that have time as an x and v as a y. So what this allows me to do for part A to find a linear model is I can take the information and put it into points. 5 years after the purchase, the value is $60,000. So my t time is going to be in years. Let's let it be 5. And let's put value in thousands of dollars and let it be 60. You could write it down at 60,000 if you wanted, but I like the smaller number. Let's let it be 60. My other point is going to come 8 years after its purchase. It's depreciated to $42,000. So my T is going to be 8. My V is going to be 42. Now, what this allows me to do is to come up with slope for my line. Remember, either point slope or slope-intercept form. We're going to put this in slope-intercept form for the assistance of our calculator if we need to. Slope-intercept form, we need the slope and we need the intercept. So how do we find slope? We do change in y over change in x. So this would be 60 minus 42 over 5 minus 8. And then we can simplify. So this would give me negative 18 over negative 3. Sorry, this would be positive 18 over negative 3. So positive 18 divided by negative 3 would be negative 6. So my slope is negative 6, which means if I put this into slope-intercept form, let me go ahead and write this in function notation. So let's let v of t, so v is my y, t is my x, equals negative 6t plus b, and b is the y-intercept. So now if I want to find the y-intercept, I can take any of these points where I know v and where I know t. So let's say the value is 60, I can put that in. That would be when the time was 5 years. Okay, let me go ahead and put that in years for time. And now I can solve this for b. So if I want to solve, I'd simplify the equation. 60 equals negative 30 plus b. Add 30 to both sides and get 90. So b equals 90. So my equation here, v of t, the value after some time, is going to be negative 6t plus 90. So basically, we're writing a linear equation based on 2 data points. We have to use those 2 data points to come up with the slope, and then find the y-intercept. So now we can write a function or a linear, it said a linear equation. You could do an equation, but we made a function that represents the depreciation. Now B says to discuss the slope. Well, we already found the slope. We know what that value is. That value is negative 6. So remember, slope is change in y, which my y is my value, over change in x, and my x is time. So I'm going to go ahead and put negative 6 into a fraction. This would be negative 6 over 1. So the slope is negative 6 over 1, which means that every year, when time is 1, the value decreases because it's a negative number. It's going to go down by 6. Now remember, we said value is in thousands of dollars. So the value decreases by $6,000. So again, if we know that slope is the change in y, or value, over the change in x, or time in this case, we can take that fraction and put that into kind of a language of what those numbers represent. C says to, C, B also, sorry, I missed part of B. B also asks about the y-intercept. So the first part was slope, and then the second part is the y-intercept. Y-intercept here, remember y-intercept is, it's 90, but remember we said y-intercept is basically when x is 0. So the y-intercept can also be written as v of 0. We saw that in the previous unit where we were looking at function notation. So basically, if I write it like this, I can say that my x value is 0, my y value is 90, or my time is 0, and my value is $90,000. So it says discuss the slope and y-intercept in context. So the y-intercept would be $90,000 was the initial value, or how much the press cost when it was brand new. So the y-intercept is always going to be when x is 0, that initial amount. So in this case, initially it cost $90,000, and then the slope tells us that it depreciated $6,000 a year. In C, it says, how much will the press be worth after 11 years? So 11 years, remember, years is time. So what I know here is that T is 11. So basically, I want to find V of 11. So I'm going to take negative 6 and substitute in 11 for T plus 90. And I can go ahead and go to the calculator if I want to. So negative 6 times 11 plus 90. The value would be 24. Remember, value is in thousands of dollars. So the value would be $24,000 after 11 years. Now question D. Question D says, how many years until the equipment is of value less than $9,000? Less than $9,000 tells us we need an inequality. So for D, we want the value, or V of T, to be less than $9,000, or just 9. Remember again, value is in thousands. So I can substitute and set up an equation here. Negative 6t, or an inequality. Negative 6t plus 90 is less than 9. I would need to subtract 90 from both sides. So negative 6t is less than negative 81. Then I need to divide. So negative 81 divided by negative 6. Remember, with t, I need to, or an inequality, I need to switch that inequality sign because I divided by a negative. So t has to be greater than 3.5. So more than 13.5 years. So it's going to take a little over any amount of time, but a little over 13 and a half years. Not equal at 13 and a half years, because at 13 and a half years, the value is 9,000. We wanted the value to be less than. Finally, the last question, E, says, is this equation valid for t equals 18 years? Why or why not? Well, let's take a look at what happens when t is 18. So in E, if t was 18, that means I'd be looking for v of 18. So I'd take my equation and substitute in for t. Negative 6 times 18 plus 90. Well, if I type that into the calculator, negative 6 times 18 plus 90, my value after 18 years would be negative $18,000. Can that happen? Well, no. So this model does not work for 18 years down the road, because the value can actually not be less than 0. What we'll find eventually is that depreciation will be what we call an exponential function. So we'll see what happens as we get closer to 0. We'll do that later in the year. But for right now, if this were our depreciation model, it would not work for 18 years because the value would be less than 0. So here in problem 10, we created our own model based on 2 data points they gave us. We created a function, and then we used that function to look at what slope and y-intercept mean, and evaluate for some length of time, 11 and 18 years, and also evaluate for the value of equipment at $9,000. So we can use linear functions in a variety of contexts. We could have also solved these problems, C, D, and E, graphically. If we wanted to graph the line and then find our solution that way, that would be acceptable. When we get to class, we may take a look at working through this graphically as well as algebraically. This is a good place to stop. So we have completed the FG.2 notes, all on linear functions. We will continue in class with more examples if needed, and then working on the homework. Thank you guys for tuning in, and I'll see you soon.